if you could run lean enough and still make power, everybody would be running 15,000. Big boost pressures, big compression ratios. We're at a level in the science where it's very, very cutting edge. People haven't really played in this realm before.
Welcome to the HPA Tune In podcast. I'm Andre, your host, and in this episode, we're joined by Micah from Redbull Powertrains. It's not too often we get the opportunity to interview someone who is working within Formula One, so we really welcomed the opportunity to get Micah onto the podcast and dig in deep to the technology behind Formula One power units. These are, of course, incredibly complex units. We also need to understand that Micah, working for Redbull Powertrains, is under a number of NDAs, so the depth with which we're able to go in some areas is of course limited, and I'm sure you can understand that. There is still a huge amount of juicy detail in here, which is going to be perfect for any of the Formula One tech nerds. In particular, we learn how Micah got his start with a mechanical engineering degree. We learn about how he got his start with Formula SAE and how he developed this into his own business before getting involved with the likes of Roush Yates, and then of course finally Redbull Powertrains. We learn about the architecture of the current 1.6 litre V6 turbocharged engines that are running in the Formula One cars this season, and we also learn about the changes that are coming about for the 2026 rules. We learn about how Redbull Powertrains go about developing and validating a new engine in what is obviously an absolute cutthroat industry where every single horsepower matters. We also talk about some of the limitations in making that power, specifically around the fuel mass limits for a race and the fuel flow limits, and how these actually play into what the teams are able to do with their engines. Now, before we jump into our interview with Micah, for those who are new to the HPA Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build and tune performance engines, how to design and construct reliable wiring harnesses. We also cover race driver education, race car setup and optimization, data analysis, and fabrication. You can check out all of our courses at hpacademy.com/courses. Relevant to today's chat with Micah is our suite of engine building courses, and obviously, no, we're not going to be able to take you through these courses and have you building Formula One engines. That's obviously a little bit unrealistic. However, if you are considering a repower on your own project car, maybe you want to get into building your own engines, this is the perfect place to start. We've got our Engine Building Fundamentals course, which will teach you the fundamentals of performance engine building. In particular, you'll learn about the operation of the internal combustion engine. You'll learn about the parts involved and how they interact. You'll also learn the common machining operations that you're going to need when building a performance engine. You'll also learn about the different clearances and tolerances inside the engine, specifically how you may need to alter some of the factory clearances when you are building a performance engine that's likely to make maybe 2 or 3 times more power than it was intended to do in stock form. Moving on from our fundamentals course, we also have our practical engine building course. Now, this dives a little bit deeper into the actual assembly process. We know this can be daunting when you're building your first engine, and what we've done is broken the process down into the HPA 10-step process. By doing this, each of those individual steps is relatively quick and easy to complete. In no time, you've got to the end of that 10-step process. You've got a completely assembled engine. You're going to have the confidence that every clearance inside the engine is correct for your application, and you're going to know when it comes time to start that engine for the first time, it's going to provide great power, great torque, and great reliability. Within that course, we also include a library of worked examples, which is an informal walkthrough of that 10-step process, where you can get to watch the process being applied on a variety of different engine platforms to expand your knowledge. I should note here that this course is generic, so it doesn't matter if you're building a twin-turbo V8, an inline 4-cylinder that's naturally aspirated, or anything in between, it is 100% applicable. We will put a link to those two courses in the show notes if you are interested in learning more. As a podcast listener, you can use the coupon code podcast75. That'll get you $75 off the purchase of your very first HPA course. Worth noting here as well, we offer a 60-day, no questions asked money-back guarantee on all of our courses. If you purchase a course and decide it's just not quite what you expected or not right for you, no problem, let us know. We'll give you a full refund. All right, let's get into our interview now. Welcome to the podcast, Micah. Thanks for joining us. Great to have the chance to interview someone that is involved intimately with Formula One. And I want to get started, as we always do, by getting a sense of your background, how you got involved in the automotive industry from the get-go. So, yeah, fill us in a little bit.
So I was one of those kids that started off tinkering and taking everything apart and managing to put it back together. Got into bikes and racing BMX bikes, and then into mountain bikes and RC cars and all that sort of stuff. Kind of natural progression. Started working on cars with my dad, and that turned into a thing once I turned 16 in the U.S. Actually didn't really care about cars. I didn't get my first car in my license until I was 17, and rapidly went downhill. Began borrowing my dad's Corolla SR5 more frequently, the old rear-wheel drive Corolla. Got into WRC and saw that and bought my first Subaru and built my first turbo kit and running around on a Haltech and as a senior in high school. And the WRX came over the States, so now I'm dating myself so people can do math will know how old I am. Ended up parting that out, and that car died in a wreck, and bought a cheaper 94 sedan and a 02 WRX engine, because the WRX engine was probably so much better than what we had in the States at the time. So my little EJ18 turbo went by the wayside, and it kind of went downhill from there. Went off to college, actually built that car in college, joined the Formula SAE team, or Formula student for the international crew out there, and it really just accelerated from there.
All right, well, let's sort of dive into a few of those details. So it sounds like you were getting your hands dirty and doing a little bit of everything there. You say you built a turbo kit.
Mm-hmm.
I'm guessing you're actually spannering on the car as well. You mentioned you've got a Haltech in one of those Subarus as well. Were you also dabbling with the tuning side of things?
I was, and I was terrible at it. Calibration, not exactly my strength, especially as a kid who's trying to figure it out. Had a buddy back in the day, Matt, who used to on the keyboard, and he was a bit better. He was a Honda guy, but we got by. So it was a 96 coupe, which in the US is not rare. But yeah, it was a little T28 T3 air research turbo and a top mount intercooler hand me down from a JDM Subaru, and I don't remember what Haltech it was. This is probably a 2000 model. You'd have to look up their ancient catalogs and see what it was. But yeah, had a rising rate fuel pressure regulator because fuel injectors weren't available like they are today. Back in the days where people are cutting caps off of fuel injectors to get more flow and all the horrible things we used to have to do. Or you got the good old RC 550s or something. But yeah,
those were the days.
Oh, yeah.
Don't take us back. All right, so moving on to college, you've obviously got this passion building for cars, but what were you actually studying in college?
So mechanical engineering, that kind of just fell into naturally. Went along with the tinkering, the hobbies, and the things I did. It's really then fueled it even further when I joined the Formula team, because the things you're learning in class, you're actually applying in the real world to something you're passionate about. So for those that don't know, Formula SAE or Formula Student is where, in my era, before the electric version was out, it was you built a little scaled down Formula One car, usually using an ATV or a motorcycle engine that's sub, I think, 610 cc's. That's what they set the rules at. And you have an air restrictor and all the other things and the design concepts, all the suspension, the engine, the aero, the body, etc. So it's really, really good building block to kind of figure out what part of the cars you're really drawn to.
That's a fairly broad project. We've talked to a few people on the podcast already involved with Formula SAE, so those who have listened to all of the episodes probably have a reasonable idea.
Okay.
It is pretty broad, though, essentially the complete design of the car from the ground up, including suspension, aero, the engine, the calibration, etc. What specifically were you involved with on your particular project?
So first year, I just kind of joined the team, throw your hand in, help with anything, basic fabrication stuff, brackets for this, cutting that, prepping this for weld, etc. Just being in general involved, scaling the car, corner weights, all those sorts of basics. Dropping strings and doing alignment, all the things you guys run through, and part of why I really like you guys so much is you make this stuff that either someone really had to dig out and find, or it's the ways that some old guy taught you, and it's making it so approachable. and so I shouldn't, more so than approachable. It's easy to access. So
We're
that's
trying.
yeah, it's fantastic. But so that was first year. Second year, I got into brakes and controls and some of the ergonomics. So doing all the calculations for sizing the brakes and your effective brake rotor and coefficient of friction, the brake pads you have, and brake force through basically the entire system. Of course, getting every driver to be happy with, oh, the brake's too heavy, the brake's too light, that side of things. But next year, I was in charge of the controls and ergonomics group, as well as started dabbling on the engine side a bit. And this is about the time I was taking my high performance piston engines course. So I have a motorsports engineering minor. So got really heavily into that, doubled down, ended up my senior year running the power and energy lab for the pistons engine course, where we had a single cylinder dyno and a bunch of Briggs & Stratton animal 8 horsepower engines where everybody takes them apart, fixes on them, grinds the port, tweaks them, plays the parts and do all the calculations ahead of time, what gains you think you'll see, kind of where your project went awry or things you learned from what you didn't account for in your earlier calculations. So everybody's learning, and that was a lot of fun. And so my senior project engine ended up being an old Honda MC22. It was the Honda CBR 250RR engine, little 4-cylinder guys, and little inline 4, and had a Garrett GT12 for it that never showed up. So that was heartbreaking for a while. Then it finally showed up. So it didn't show up in time for competition or anything. So my senior project engine never actually ran in anger at competition because I left in my gear. Also, like a good core of the team all graduated that year as well. Some of my best buds who we still keep in touch with. Yeah, so unfortunately, those 3 engines all sat, and they've all slowly grown legs and left the university somewhere. I'm sure someone's got them sitting in their garage now, but
That's a shame.
yeah, I know.
All right. You've just mentioned a bunch of really interesting aspects, and it sounds like this university that you went to is the dream location for anyone with a passion for motorsport in particular. So you mentioned a piston engine design course. I can't quite remember what you actually called it there.
So Old Dominion University in Norfolk, Virginia, they offer a high-performance piston design, high-performance piston engine course.
Okay. Can you give us sort of a breakdown on what actually that covers? Because again, that could be quite broad-reaching.
It is a lot of applied thermal sciences. I'll put it that way. It might sound really cool on paper, but it's really getting to the nuanced level of engineering, calculating, going through the thermal cycles, and understanding how everything works and applies, and heat rejected, and all the things that go into designing an engine, or at least beyond not so much designing, but even just understanding what's going on. So, from a development engineer point of view, someone who runs the test cell, just getting data, when you throw more timing into something, all of a sudden you get more heat rejected. Well, why is that? Well, you start getting in all the sorts of things, efficiency maps and all the other things that come into a general engine performance for like a road going car. If you were to take a road going car, at what RPM would it be ideal to actually cruise at, where you're actually at best fuel efficiency versus something else?
Okay.
So it really kind of gets in the theoretical side of it. And then the lab was the hands-on part.
So talk to us a little bit about that lab. I'm assuming you're spending a lot of time on dynos with these engines, testing and validating changes.
So we had an old Landon C. Well, it wasn't old; it was new at the time, but now they'd be old. And Landon C is not even around anymore. So a single cylinder, essentially go-kart engine dyno that they made. So it was a water brake. And yeah, I was in charge of setting it up and getting muffler system routed for it and getting the lab set up. It was the first year they were going to have it running. And so we had, I think, like 20 different Briggs & Strattons. They came out as a partner with the school and donated a bunch of engines. And so I had a bunch of engines and kits and setting them all up and speccing them all and getting them all running and all of them tuned up and intolerance and setting lash and getting all the little bits. And you start looking at the head, and we had a flow bench. And you start looking at the head and seeing, well, it's a mass manufactured head. They're doing this cheaply as they can. It's a lawnmower engine. They just want to get this thing clapped out and running. What things could you do to improve it? If you were to reshape the combustion chamber, what would you do and why? If you put in a high compression piston, what trade-offs would you get? What thermal efficiency gains do you think you get by putting 2 points of compression in? What would they do to your fuel? How about your timing curve? And timing curve became a thing that we have to set up because it had a magneto in the flywheel. It's stupid simple. So we had to put on a different flywheel, put on an actual ECU, and all the things that went into setting it up and kind of understanding the engine at a basic level. And so we broke off into groups. And the groups, everybody have their design concept that they wanted to do, and then you'd have to go about executing that and comparing early calculations to what came out and where you went horribly wrong. You put in 2 spark plugs and you thought it was going to cut, flame propagation in half because they're coming from 2 sides, but it doesn't mean you have twice the cylinder pressure. Oh, well, hold on. Yeah. So all those really early things you might learn.
So it sounds like your on dyno validation didn't always stack up with your expectations.
Well, no. I mean, that's part of it. No one's perfect, and you got to learn at some point, right? But also because I managed it, I also got to run all the other engines too to see where they were. So it was wild. It was even out of the box. Some of them were like 4.5, 4 horsepower, like way down. lash is horribly out. They're not even close to base circle. They're like coming on low, like halfway through lift. It was pretty bad out of the box. So if anybody's buying a Briggs and Stratton racing go-kart engine, please take everything
Check your
off and
lash.
check it. Yeah, check your lash for starters.
Okay. Well, I mean, obviously, this sounds like it sets you up perfectly for your career that you're pursuing at this point. I also wanted to talk about you mentioned a motorsport minor as part of your degree. So
Right.
what does that actually entail? I mean, obviously, if we come back one step, mechanical engineering in and of itself is a very wide field that can be applied to a bunch of different industries. So this is kind of streamlining it more towards a motorsport application. Is that what I'm sort of reading from that?
Correct. They actually have a motorsport engineering bachelor's now as well. They didn't have that at the time I was there. But I would still recommend mechanical engineering because it is, as you said, not just broad in industry, but it's a very broad study of various fields of engineering. So you'll get into different fields. Obviously, someone who's going to be an electrical engineer is going to have way more knowledge about setting up any type of circuit board than I would, but I have a basic understanding because you have to do that. Or a civil engineer is going to be able to run circles around me. One of my buddies from FSAE's civil engineer does bridge inspections. If I design a bridge, I would just go to Alex and ask him to check it out. But yeah, so you have the fundamentals and the understanding. And even if you're not the expert, you know someone who is, or you at least know the right question to ask to get the expert's answer. Then yeah, the motorsports degree is the same. And there are a few of them that pop up. What we had was a joint program called Viper that Eric Koster, my old mentor, he built dirt track engines and all kinds of asphalt engines and stuff. He was a V8 guy and also always the turbo guy, so we're always butting heads on design and concepts for Formula C engine. But the Viper was a joint program that we had with Virginia Tech. So Virginia Tech also has engineering program as well. And in the middle of us is Virginia International Raceway. And so out there we had a dyno, and if I recall, Tech ended up getting a 7-post shaker rig. And so between the two, you have that, and combined they had a Motorsports Masters you could get as well.
Wow.
So options galore.
Absolutely. All right. Well, let's sort of move through a little bit further in your career. What have you sort of done as you left college with your degree? What was your first step from there?
Leaving college, a bit different than as I've learned here in the UK. So in the UK, they do a lot of times they do a year away or study abroad sort of thing, or they'll pop off. And so, for instance, I've got a student who's in my team, picking up fantastically, goes to a good school, guy's got bright future ahead of him. But in the meantime, all of his studies are in time out because he's off working for a year. So in the US, we'd call it co-op. Where I was positioned in Old Dominion, I was able to work through school the entire time. I had an intern at NASA Langley, and then was moonlighting. I was working NASA Langley through ODU, through the Research Foundation. And then, so at the wind tunnels that they have there, so the 60 by 30 and the 14 by 22, did a lot of work with Penske, both north at the time, which is well, they're still IndyCar up north before they moved to Mooresville, and then Penske south, which was in Mooresville for NASCAR. Occasional drag cars, top fuelers, all kinds of interesting stuff would come through. The wind tunnels, not for me. I had my head into engines, so I was gone. Moonlighting at a dyno shop in Virginia Beach. It was called Dyno Inc. at the time, so I was out there helping set up a couple hours a week and on the weekends. So probably working more than I should have been and not studying enough. But ended up getting really, really heavy into Subarus and Subaru engine design with my buddy Dom, who's there. He was a Navy nuclear engineer at the time, and he's off running his own shop in Idaho now. We got into doing D-stroke Subarus, literally discussion over the kitchen, dinner table. That had to make more power. Well, let's go and make a big bore EJ207 essentially, because we had the EJ205. We hated the power delivery from them. The good old 2 liters would rev and make power. And so I started with that stuff, kind of turned into my hobby business. And so I started that right out of college called 3MI Racing. Kind of did that strictly as a hobby, tinkering, keep my other ground, design bespoke engine parts for guys that wanted them, fixes for motorsport related Subaru problems, which Lord knows they have plenty of them.
Yeah, that would potentially keep you quite busy.
Yeah. So that was my evenings and weekends. And if you want to get good at, designing an engine, start with a really bad one and find all the things that go wrong and go, I won't do that again. But no, I still love Subarus. I think I have 4 of them now.
Wow.
Trying to keep track. Naturally, I moved over here and bought a GS8 because, needed the space and it was cheap and I know Subaru. So started out of college, did a quick stint doing QA for steel chainsaws at one of their sub-assemblies. So got into quality assurance engineering. Absolutely hated it. Bored out of my mind, but it was a job and I needed something. So popped into it, quickly transferred over to a place called Bush Vacuum, where I was an R&D engineer. So did a lot of testing for custom vacuum pumps and vacuum systems for everything from pharmaceutical to college laboratories to vacuum arc remelt facilities, foundries, and everybody in between. So it was a pretty interesting experience I got. Then the recession came around. They started doing layoffs everywhere, and I was one of those people. And so I fell back on doing my own thing because I still had 3MI in the background. Ultimately, ended up getting picked up to go to a Volvo Powertrain in Hagerstown, Maryland, where I went to go do diesel engine calibration work, so performance and emissions work. And so that was quite interesting, falling back in on the calibration side of things. And that's really, really when I started sinking into it. And there's a lot that goes on with it, but calibration isn't for me. Left there, ended up going to Volvo Pinta, still as a contractor for Volvo, doing gasoline engine design for their marine side of things, so stern drives, etc. All in the background, still doing 3MI. I left there to go to Roush Yates engines, so go design race engines for Ford. So I got picked up to start on the engine design for the Ford GT. That went on to win the 24 Hours Le Mans in 2016, which is the whole purpose of that project. Did a little bit on GT350 work there, so the flat plane crank Mustang engine, the Voodoo engine. That was basically a GS class engine, so we didn't really have to do much. Had a dry sump on it. That was about it. Little things would pop up. Brackets. It's a funny story. We had to make a bracket to lock down the head of the starter because they were killing starters in about 10 minutes of track time because it was shaking so badly. So ended up having a bracket that goes on the end of the starter that kind of ties it into the block. Yeah, it's a goofy little thing. But yeah, guys show up from the track, put a starter. I have a starter on my desk in a box. Like, we have a problem with this. Like, what? You pull the cap off and, all your little copper connections that go to the brushes were just balls of copper that had been bouncing around the head of the starter.
So is this a vibration-related failure mode?
Yeah, vibration-related.
Okay.
Well, if you have a vibration, either you find a way to, kind of two simple rules is you either make it stiffer or you make it lighter, right? So if you can't make it lighter because it's the starter that you use on umpteen different vehicles in your product line, you're not going to change that. So you find a way to make it stiffer. So you tie it to a node that makes it now locked down, so it's no longer sitting there shaking away.
Sure. Yeah.
And dancing. So yeah.
Okay. So can we just talk a little bit about your time at Roush Yates? Obviously, big name in the performance motor industry. So what? Obviously, you've talked about this little bracket for the starter motor with the design of the engine for the Ford GT. Sort of what was your involvement in that particular project? I'm guessing that these projects are teams of people. You're not involved with the whole thing from start to finish.
Yeah, so I was largely so I was a design and analysis engineer there. And the way that they run things is we have a design and analysis department where there's 3 full-time CAD engineers working on things. So my buddy Jason, at the time I started, a guy named Sean, who's really a machinist, but he knew CAD well enough to come over and fill the seat because they were short-staffed. Jason was full-time on NASCAR stuff, and I got hired, and I was full-time on Ford GT. And Sean was in between us, and he was kind of working where he could. They ended up hiring another guy, Greg, who still keep in touch with. Good guy, and he came on to kind of help finish out all homologation side of the Ford GT, that program, the Phoenix program. But yeah, as you'd expect, you're kind of taking a production engine and turning it into a race engine. We started with the early, it was the MY17 as they called it, what was supposed to be the engine going into the GT is what we started with. It was really early. I mean, Ford was still working on their stuff and changing castings and doing all kinds of revisions, and it was just me working on, say, for instance, they did a new head release on top of all the other parts I have going. They did it because they've got an army of engineers. They changed the head. I now have to get this head and do all the updates we did to put in, a secondary high pressure fuel pump. So we had high pressure fuel pumps on both heads. The engine, the billet caps for that, the port work in it, all the changes you end up doing in this head to make it a race engine. So we ended up running the MY17, didn't make the power we thought it was going to compared to the MY14, which they'd already been running for the Daytona prototypes. So the project pivoted to updating the MY14 style engine for the GT to go racing. So, different valve sizes, slight overbore, all the things go along with it, specking your cams, intake manifolds, valve covers, front covers.
Sure.
Of course, the dry sump system, integrating that into the block, all the things that go along with it, block modifications for actual piston oil squirters, more real piston oil squirters than what you get on an OEM engine. In that, so to explain a bit, most piston oil squirters from like an OEM, you get like maybe one jet that's shooting at the piston. When you start getting race engines, well, for instance, say you have a boxed and shredded piston where you have all these separate windows. If you're spraying oil, up along the skirt and it might be going across the crown, if you're lucky, it might get the other side of the skirt. Realistically, probably not going to. You might get some on splatter, but you're going to spray it and just kind of, spray and pray that it does good enough. When you start getting into the race engine side of things, it's you really have a jet dedicated to each pocket of the piston.
So multiple jets.
So yeah, multiple nozzles, correct.
Now let's just talk a little bit about the under piston oil squirters. So These are
Yep.
for cooling the piston crown, correct?
Correct.
So not a lubrication element. And I mean, as you've mentioned there, we do see under piston oil squirters in all manner of road-going engines. And one of the questions I do quite often get asked, and I mean, this is more in line with, modifications to existing road-going engines to turn them into race engines, not bespoke race engines, is should we retain the under-piston oil squirters or block them off? The school of thought there is that you are using oil that would otherwise be supplied to the likes of the main bearings, and you're not going to have as much oil volume or pressure as you would if those were blocked. The other element I quite often get asked about is oversupply of oil to the bore walls, and whether that can make it harder for the oil control rings to actually clear that oil off the bores, and then leading to oil consumption. I mean, the very fact that you say so much went into this, obviously there's an advantage there, but I'm just interested to get a little bit more sort of background around it from you.
So part of the reason, the why you do it. So all valid points. If you had a pump that was already struggling to keep with oil flow, taking more oil flow and throwing it at a piston, well, you might prefer to actually keep your bearings alive. But part of the reason you end up doing it is you have all this heat going to this piston. You usually go to a race piston and it's a smaller skirt and reduced, well, I'll say, contact area with the wall. Not that it's actually rubbing the cylinder wall, because it was actually contact, it's bad, but you have the oil film and heat is getting rejected and transferred to your bores through it, obviously to some extent. But you have a mass amount of heat that's going into the top of this crown. And for those that don't know, I'm sure a lot of you do, if you've ever actually measured a piston is not round. A piston is an ovate shape, and you look at it from top down, it's kind of shaped like a barrel. It starts skinny at the top and gets a little bit fatter, basically just before you're going to run out of skirt. So a little bit above the top of your skirt is usually where you have the fattest point in your piston. And depending who you speak with, this is a skirt profile, or it's called cam on the piston, or it depends on usually how old a person you're speaking with and how it's being actually manufactured to cut these shapes.
An important element with that is if you're installing an or any piston for that matter, there will be a measurement point that the manufacturer gives you on the skirt. I think it's often referred to as the gauge point. So that's to measure that widest point, and that's where you're setting your piston to cylinder wall clearance. The idea behind this is that when the piston is actually at operating temperature, that cam or barrel shape is designed so that when the piston actually expands, it's obviously not going to expand evenly, and that then gets us essentially parallel to the cylinder wall. Is that the idea?
Yeah. So the concept is that then it becomes more square, and your piston essentially starts to tighten up a bit. If you have, I'm sure many people here had a forged piston where they put it in, and a lot of, I'll say, aftermarket guys, manufacturers would rather run a more aggressive cam, have more taper in the piston than what's really necessary, because it means some guy's going to run this at 400 horsepower, the other guy's going to try and make 800 horsepower on it. The amount of heat going to that piston is worlds apart, but they're going to design one piston to do the job for what the aftermarket wants. So when you start getting to developing a piston, you start developing that profile, and you start watching on teardowns how it's wearing and where it's wearing, and you kind of get an idea of how it's fitting. But yeah, so the thing is, you end up having that heat, and the more you can get it dialed in to being a close piston to wall, you're good. The other problem you run into is with aluminum. Most aftermarket forgings, high performance ones, be 2618. It does quite well at heat, at temperature. But even then, at elevated temperatures, its yield drops a lot. The strength of the actual alloy drops a lot with temperature. So the more temperature you can get out, the better off you are. The more temperature you can get out when you're designing a piston, then essentially the stronger the material is, because it's now at a lower temperature. It's closer to your, best case, say it's running at oil temperature. That's as good as you're going to get. That's going to be world stronger than, say, if it's running at, well, let's see, you want Celsius or Fahrenheit? What word are we talking in here?
Let's go Celsius, because I understand it.
Yeah, I didn't know. I always work Fahrenheit in my head and have to convert. But we'll go ahead and say just generic track car. So you're going to run 100, 110 C, and if you go ahead and bump on up to like 150 C, that's a world apart. You're getting where oil's breaking down and everything else. That piston, however, is also at that same time dropped off grossly in strength. So to keep its strength up, you have to have more weight, a thicker crown, everything else. So in the best case, if you could have this thing running ice cold, you could get away having a thinner crown. And because there's no heat going into it, because you're keeping it ice cold, your starting position would be closer to an actual square profile and less of that barrel. So it makes it easier to control a piston to wall and have it in a happy space to keep your piston alive.
Yeah, that makes perfect sense. I guess another element for the road car people listening as well is we have to understand that the the heat being introduced into the piston for an endurance race engine is dramatically different to what we'll see
Right.
in a road car application where, if you value your license, it's probably difficult to stay at wide open throttle for more than 8 to 10
Yeah.
seconds in a powerful car.
Yeah.
So they're very different applications, and obviously there's considerations around that. Also, you mentioned about the oil pump and its ability to flow sufficient oil volume. Well, of course, that's can be an issue with a factory oil pump, but in a racing engine, we're always moving to a dry sump
Right.
where the pump is got more volume than, or is designed with the correct volume for the application, correct?
Well, so yes, for most, I'll say your performance aftermarket. Yeah, you go to a dry sump pump and you'll call up Daly or Peterson, whoever you're going to for your dry sump pump, and you call them up and they'll give you a pump that's plenty healthy for you to go ahead and run without an issue. At the racing end, you always try and back off the pump as much as you can because it's lost power that you don't want to use if you don't need it. So the other things in relation to that, when you end up a lot of OEMs, you'll see where they have kind of like a check ball behind the piston squirter, so that at low RPMs you're not losing all of your pressure through these holes that you have. So you get to a certain point, pressure blows open, it starts opening up, jets start spraying at higher RPM, usually where your pump's already at capacity, might already be getting close to opening its own check valve, so you're not overpressurizing the system for whatever they set it to from the factory. So all that kind of goes into it.
All right. I think let's get to the crux of what we obviously wanted to talk about here,
Okay.
though, and that's your experience with Formula One. And as I understand it, you've sort of recently moved to Milton Keynes in the UK, and you're working for Redbull Powertrain.
Correct.
Is that how did that sort of come about?
So I had left Roush Yates and was doing my own consulting, performance aftermarket, designing parts for Lamborghinis and McLarens and performance shops. And I knew from the grapevine that this Honda deal was coming around and Red Bull was talking about doing their thing. And at this point in time, my wife had gotten addicted to Formula One because of Drive to Survive, ironically. So
How about that?
yeah, go figure, right? So I'm here because of Drive to Survive. So my wife was cool with it. But
I think Drive to Survive's got a lot to answer for these days. Definitely a new crop of Formula One fans.
Oh, that they do. But no, so I'd already been a Formula One fan. But it's one of those, the opportunity came along and, threw my hat in the ring and ended up getting a call and had an interview and job offer, and here I am. So, and I get a lot of people to ask, how does it work? Well, you just apply and it's an interview. It's like any other job. Like, it's not
There's
like
no
you have
magic
to know
here.
somebody. No, there's no magic. They think there's something like, how does you have a skill set they need and apply to a job, and they say you're the man for the job or you're not. It's that simple.
Yeah, I think probably a lot of people think that, well, they do hold Formula One up on a pedestal, but at the end of the day, as you say, I mean, they're looking for people with the correct skill set. If your skill set matches,
Right.
well, yeah, just like any industry, really. All right, now I'll sort of clarify here. Understandably, I'm guessing most people will be able to figure this out. There's a lot that you can't talk about in detail, and that's understandable. But we can still talk a lot of general high level concepts about Formula One engines, their design, their development, which even at a high level, most people aren't going to get the insight that you're able to give us. So there's still going to be a lot of great stuff we can talk about. I think to get started, for those who maybe aren't following Formula One in any sort of detail, can you give us a little bit of an overview of what the current crop of Formula One engines actually entail? So what are we talking in terms of the engine design that is currently running?
Currently running, it's a 1.6 liter, 90-degree V6. So you're talking, it's 266.7 cc's per cylinder, give or take. They're limited on bore size, rod length, therefore stroke, and essentially within reason deck height too, if I recall, they have for the current regs. And a little fuzzy because I'm working off the 2026 regs. These engines have what is known as a fuel flow restriction that is controlled instantaneously through the rev range. So as the engines increase in speed, they get increased flow rate until it caps at the current regs are 100 kilograms an hour at, if I recall, it's 10,500 RPM. And so, a lot of people wonder why these engines aren't screaming to all kinds of RPM and making all kinds of power, because they're allowed to spin to 15,000. And so one of the reasons is because you literally run out of fuel. You just can't go any further and still make power. you can make power as far as you can.
There's no benefit at the moment in running the engine all the way to the regulation RPM limit. Is that what you're saying, because of that fuel flow limit?
Well, there would be if you could run lean enough and still make power. Everybody would be running 15,000. It just gets to a point of being able to. We're at a level in the science where it's very, very cutting edge. People haven't really played in this realm before.
Yeah.
Big boost pressures, big compression ratios, and you try to get it as far as you can. And you see some of the teams are peaking out 13.5 or so, that sort of thing. They're coming up. And you think of where they used to be back in 2014, guys weren't revving really much past 12.
Okay. So there's advancements being made in here.
There are. And the other things that come along with it too is, you think you're spinning RPM and you're not really making much power. Friction goes up pretty much exponentially with given speed. So either you're making power or you're losing power, and then you're just wasting energy. And this whole thing is about energy at this point. So because you have a set amount of fuel, you have a set amount you start the race with, you have a set amount you can burn at any given time in the power band. If you're not going to make power in regard, efficient power, it's not really cost worthy. This is the reason you don't have pops and bangs, anti-lag and stuff. Well, they have an NGUH right now, but it would make sense because it's a lot of fuel for not necessarily turning it into shaft energy or stored energy in the battery.
Yeah. I think the fuel flow limits and the limitation on how much massive fuel the car is allowed to start a race with, are easy to overlook in terms of limitations on how efficiently we can essentially turn that massive fuel into power, which is really one of the keys here. And I hear in rough terms, a modern road-going internal combustion engine might be somewhere in the region of maybe 30 to 35% efficient in terms of how it converts fuel into power. And the numbers are sort of here for the modern Formula One engines. I don't know if there's too much accuracy in here, sort of 50% or above. Is that sort of in the ballpark?
I mean, I know Mercedes came out a few years ago saying that that's where they were, and with knowing where everybody else in the field is, I would say, you look at the power Ferrari's making now, and you look at the power the Hondas have come up making, whereas Mercedes used to be like this dominant force. And I'd say, yeah, the only way you do that now is by catching up on the efficiency, because you haven't gotten any more fuel. None of these guys have gotten a fuel increase, and now they've had power increases, so obviously that efficiency is gained. To what exact percent, I'm not sure. But my world lives off of cylinder pressure and how many kilowatts we're making, so we're not too lost in the thermal efficiency side of things.
Sure. Okay. So it sounds like from what you've mentioned there that there's a very stringent rule set that doesn't offer potentially a huge amount of flexibility in terms of the geometry of the engine for starters. Yet we see a wide range in engine performance across the different manufacturers. So where are the key areas that are sort of ripe for development? Where are you getting these benefits from?
So yeah, the base architecture is very much locked down. I think the FIA did that as a point of focusing the teams and having certain, I'll say, areas be where they're emphasizing. So obviously combustion systems being probably the biggest one of them all, in my mind, as a obviously piston engine side of this the scenario. I will also say battery cell technology is another massive push that they have on the ERS side. Your storage and containment and the efficiencies of all those systems, because if your inverter is losing efficiency compared to someone else, that's again lost power that you would otherwise picked up. So they're doing the same thing on the ERS side of the game that we're doing on the engine side. We're making our stuff as efficient as we can with as much power. They're likewise doing the same, being as efficient as they can with as small of a unit as they can to be able to have the energy that they need and to be able to have the thermal controls for it, so they're not going to have an overheating pack. And also same goes with the NGUK. So for those that don't know, the NGUK is essentially a drive to the crankshaft, usually through some type of intermittent gear, etc. But essentially, if you want to think of it in a simplified case, it is an electric motor that drives directly to the crankshaft. The V8 era had the flybrid, whereas this hybrid kinetic system. This is, I don't want to say it's more simplified, but in explanation, it's more simple.
I want to talk a little bit about those systems, NGUH and NGUK, a little bit further on. So I won't sort of dive into too much more detail there. You've kind of mentioned boost pressure and compression ratio. I mean, those are two aspects that we do have at our control when we're A, tuning the engine in terms of boost pressure, B, designing the engine in terms of the compression ratio. And the compression ratio and boost pressure also need to be considered in regard to the octane of the fuel that you've got available Otherwise, we potentially get into problems with knock. Are these the same considerations that are going on at an F1 level as to a modified road car level?
I'd say it's a bit different than a modified road car level, largely because we have in-cylinder pressure sensors, which currently by the regs right now, everyone lives and dies by them. They're actively tracing their engine the entire time and seeing what they're getting for peak cylinder pressures. And if they have a knock event, how many hundreds of bar of knock they're seeing. It's pretty wild. But again, the bottom end also has to be built robustly enough to take these events and not fall apart. So it is definitely a design constraint. As for designing the combustion system side, you have so 26 reg numbers. I've seen them already shared on Reddit, so this is nothing proprietary. It's 4.8 bar absolute, 16:1 compression ratio, still the same 102 RON if I do recall, and it's all synthetic coming for 26, so that'll be a big change. It's going to come with all the teams, so it'll be quite fascinating to see who gets along with their different technical partners, who has the best fuel and executes the best. But then, knock is a thing. It's something that's always in an engine, and obviously it's a big power decrease. So it is something that occurs, and you find it in your data. And at this point, it's not that it is necessarily you think from a conventional road tuning car that if knock happens, you kind of get scared and pull some timing out and go, all right, well, we found that edge. Let's back up and see what NBT really was, and we'll just live there. At this point, they're literally fighting for that ragged edge, so it's part of life, and you deal with it. And the engines also don't last as long, right? So they only have to go through so many Grand Prix.
So what you're saying there is you're using that, well, the calibration engineers, I know you're not involved in the calibration side of things, but they are walking that tightrope, and knock is going to be occurring during any lap of any race, essentially.
Yeah, essentially. So the trackside guys, my roommate owns one of those guys, and I talk with him, and it's quite fascinating how they sit there and babysit the engine at the track and what's going on and make sure it's staying and living healthy, and it's just eyes on the laptop the whole time. They're also the guys who load up the tune for the drivers, so the feedback and how they kind of want the thing to run, and they're the guys who talk with them, make sure that everything's copacetic. So
this might be a little outside of your area of expertise, but given the fact that they've got in-cylinder pressure monitoring, is it safe to assume they're using that as a closed loop knock control strategy while the car's on track? I mean, obviously, one step well above using a conventional piezoelectric knock sensor mounted to the block.
I'm not 100% sure, because this is also one of the things that part of where the Honda Red Bull thing came apart, where Honda wanted to keep all their IP. The control strategy is Honda's IP. So
okay,
all the links that are connected in the box, hit this button. What is it actually doing? That I don't know. So
yeah, no, fair enough.
So unfortunately, I can't share that fun tidbit.
Okay. All right. Coming back, one of the other elements you mentioned there for the 2026 regulations, I was sort of getting a little off track, but don't worry, I'll come back to where we were, was the use of the synthetic fuel. So can you elaborate on what that actually means and where the complexities are going to come from for the teams in getting around this synthetic fuel?
Synthetic fuels, not meaning that it's green fuel or corn grown ethanol, that sort of thing. Synthetic fuels are, I'll go and say, laboratory made fuels. Scrub CO2 throughout the atmosphere and relink the hydrocarbon. However, the mad chemists with PhDs do it. From my point of view, and where it affects my team is how it runs and how it operates, oil dilution, other strategies like things that'll come into play, and then just downright to which performs the best. Because you look at one of my favorite breakdowns is you look at kind of you have the raw chemical energy of gasoline going into this engine, and you look at it and go, where does all of it go? You have all your thermal efficiency losses, and you have frictional losses, and all these things. How much is rejected through heat? All right, well, we have a turbo to try and help regain some of that efficiency that's lost, because at least we're turning it back into shaft energy that helps, on the charge side, and then it's, increasing air density, etc. But when you have a lower raw chemical energy, it's, how many BTUs or, how many, joules of energy you have in this fuel to go in at the beginning. So I think it will be quite interesting to see where the synthetic fuels evolve, because they're still, in my experience, I've never played with them, before here, but where it's going to go and where it's going to lead once they really start getting pushed and these development loops start and the funding is there and the customers are there, it'll be really cool.
Is this going to sort of get back to the the older sort of maybe early turbo F1 era where each of the teams were sort of aligned with a fuel company, and from what I understand, there was some pretty crazy concoctions of fuels being developed specifically around F1.
Crazy amounts of toluene and all.
Yeah. So some pretty nasty stuff that you probably don't really want to be breathing. But are we kind of heading back in that direction to a degree, maybe with something slightly less volatile to human life?
Yeah, hopefully something better for human life and for the atmosphere. But I would say, yeah, I think it's going to go back that way where the teams have different strategic partners that they work with, and they'll have their spec of fuel that they run, and then I think that'll definitely be a potential advantage going into 26.
The obvious next question is, does that technology kind of filter back down to synthetic fuels for road car engines, or is that relevance really sort of done and dusted now with the obvious move towards EV?
I would certainly hope so. And to the point, Porsche had invested just recently, I think last year, maybe the year before. I want to say it was in Venezuela or Chile, a synthetic fuel CO2 scrubbing factory that they're setting up to do synthetic gasoline. I think it's a real viable option. Fun discussions to chew on is if you're taking the CO2 out of the air to put it back in the tank, that's not really an emission you have to be so concerned about anymore. NOx is, of course, still there, but again, NOx largely comes if you're running lean, right? So if you're not running lean, then you don't have as much NOx. And plus, we have ways of treating it, barium NOx boxes or, urea systems, diesel exhaust fluid systems, selective catalysts.
Yeah.
So there are all kinds of ways we could go ahead and run really, really clean. So it is fascinating potential.
So this is a technology that I do not have any knowledge about, but what you've just mentioned there with the CO, this is sort of almost emissions neutral on that element, is what you're saying. It's scrubbing that, turning it back into a fuel, but then we've got the NOx output, oxides of nitrogen, and as you say, that's sort of a lean burn or a heat-related element. But that's kind of the gist of things. So we're actually getting a synthetic fuel that is much more carbon neutral?
Potentially, yeah.
Okay.
Depending on the systems and how they're doing it. All the ones that I've seen and I've read about, we're looking to scrub CO2 out in the atmosphere and relinking the hydrocarbon chains. And yeah, so kind of makes carbon neutral at that point.
Well, it'll be interesting to see how that does develop. And I mean, obviously, Formula One has been over the life of it a hotbed for development of technologies that do filter back to road cars. So if we can keep that relevance and improve the breed throughout the entire industry, we'll happy days. Now, another technology I wanted to dive into, it sort of comes back to, again, this limitation on fuel mass that the teams have access to, and then the fuel flow limits as well. So it's really important to be able to run these engines lean. And I don't obviously have any numbers, but is it safe to assume that these engines are being tuned well lean of stoic under all operating conditions?
I'll go and say that's no secret across the grid, so I'm not going to step on anyone's toes. Yeah, we're all running lean past stoic.
Okay. Now, one of the problems with running lean, and anyone who's had a road car engine on a dyno, you sort of, particularly under cruise conditions, if you sort of lean the air fuel ratio out, you'll get to a point where you're going to end up running into a lean misfire condition. Essentially, you just can't reliably ignite the air fuel charge when it's lean. And I'm talking here about a normal port-injected engine. But we do get the same things in direct injected engines as well. There is sort of a limit to how lean we can go and still get reliable ignition. And Formula One in this hybrid era have been using this turbulent jet ignition system to help circumvent that. So again, this isn't necessarily a new technology, but can you talk us through what that is and how it actually operates?
Okay. If anyone's listening and sitting at their computer, you can look up, it's Federal Mogul, that's what they call pre-chamber spark plugs, in which what it is there's a volume with essentially small drilled hole nozzles that encapsulates the tip of your spark plug. So looks kind of like a conventional spark plug, just has this little helmet on it, and this helmet has little holes in it. And these are used for big bore natural gas generators. The reason they use them in big bore natural gas generators is to a similar reason that you would use them on a lean running gasoline engine, in that getting the flame to the far away potential fuel that you want to have oxidized and combust with your oxygen you just can't reach it. And so in their case, they use them to go ahead and get this, expansion across the bore, so you can get to the far distances of your bore in the given combustion time. So keep cylinder pressures up, keep efficiency up. Same thing in a Formula One car where you're running lean. And so even if you did the best job of having this great, air mixture coming in and everything's super well atomized, there comes a point where it's so lean and literally at molecular level, where's your gas and where's your oxygen, how many are touching it, what's a particular point, getting them to light off in a way that they rapidly grow enough. And you watch, the kernel, as you call it, your flame propagation go. So you put in the jet for the same reason. So you have this bore and everything's lean, and when your jets go off, you get this mass spread that covers the top of essentially your piston, looking top down. And so you get these jets that come out and the plumes develop and combustion happens much more rapidly and more efficiently.
Okay.
It's what aids you in running that lean.
All right. Am I also right in assuming that if we had no fuel flow limits, no fuel mass limits, that there would be a significant increase in power available by running these engines at a more, what we would consider conventional air fuel ratio lambda target?
If we didn't have a total fuel and a fuel flow rate limitation, I would say absolutely. Yeah. You turn the power up. There'd be no reason not to.
Okay. How about the effect of the air fuel ratio on the combustion temperature? Because again, this is sort of an area where there's a bit, I see a lot of misconception that, the usual theory is as we go leaner, the exhaust gas temperature, if we're monitoring that's generally at our level, the way we get a window to what's happening inside the combustion chamber. And obviously there's a lot of other elements in between what the actual combustion chamber temperature is and the exhaust gas temperature. But for all intents and purposes, let's use that as a link. So if we start out at a rich air fuel ratio, maybe 0.72, 0.75 lambda, and we look at the EGT and then we lean the air fuel ratio out maybe to 0.90 or something like that, we see the exhaust gas temperature rise. And that correlation, I think for novice tuners, those just getting involved, they're going to expect that just sort of extrapolates out. So if we're lean of stoic, then damn, that exhaust gas temperature and hence combustion chamber temperature must be through the roof. Is that how that works out?
So combustion temperature and exhaust temperature are two different things. So you think in a normal port injection engine, if you had fuel in there but you couldn't light it off so your combustion temperature is cold, you still have fuel in there that's unburnt. Now you take that fuel and stick it into your exhaust system's going to get real hot. So it's kind of in some amount goes that way. Now if you're running lean and you had really, really great combustion and you burned everything really fast at close to top dead center, you're talking you start looking at peak cylinder pressure values that are, I'll say really general numbers, not to get myself in trouble here. We'll say 15 degrees after top dead center. Not too far off from a conventional engine, 15, 17, somewhere there. Look at various books and data that's out there. You look at how far that is down the bore, you've traveled practically nowhere. But if your NBF50 is already, that far down the bore, you don't have a lot of fuel left to burn. NBF50, indicator of your total fuel fractional burn. So, had 100%, 50% of it's gone by this degree after top dead center. So that's a big indicator of performance, particularly in this realm of engine development. So if you're still having a great combustion, though you're lean, you don't have much exhaust temp. You lose a lot of exhaust temp because all that energy literally turned into cylinder pressure. The exhaust temps, I'll say some of the ones that come out in simulation kind of make me giggle, and I'm going, my diesel truck runs hotter than that. Oh, yes, it's modified and played with, but you look at it and go, that's kind of wild to see.
Sure.
You look at it and you come into it and you stop and think about it and go, oh yeah, that makes sense. Yeah.
I think
so backwards.
I think what you've just mentioned is really good to sort of drill down on, in that the correlation between what's actually happening in the combustion chamber and what we're reading in the exhaust gas temperature sensor. It's difficult to draw a really firm conclusion between the two because there are so many elements that can affect it. I mean, you've mentioned a couple there. The ignition timing we use as well is going to affect it. But I mean, at a hobbyist or even semi-professional level, unfortunately, that's sort of the tool that we generally have available to us. Let's move on, and we talked briefly about the NGUH and NGUK already, and these are two other elements that are really pivotal to the current Formula One rules. You've sort of briefly touched on them, but can you elaborate maybe for a start? NGUH, how does that work? What is that technology?
So the MGUH, put simply, is if you were to take an electric motor and stick it between the turbine and compressor on a turbocharger. Much debate for people that follow Formula One was, the split turbo where Mercedes had done it first, where they had a turbine in the back, this whole long shaft that went through the valley, and the compressor at the front of the engine. And in the middle was essentially this electric motor, so the shaft runs through it, and you basically, simplified terms of not being an ERS, expert, turn it on or off to, essentially have it regenerate, or it's passive, or you can then put flow back into it and have it actually drive the turbo. So think of it as electric anti-lag, or electric overboost, or whatever strategy you'd want to use it for. In theory, you could sit there and open your wastegates and just dump all your, electric power into said motor and just have essentially an electric centrifugal supercharger at that point almost. So that there's a myriad of ways that you could use it in a strategy. At the same time, you can use it to, keep your gates shut and drive your turbine really hard and put a bunch of power back into the battery if that's something you want to do in a given situation. So it's a big, I'll say in the game of chess, it's one of those tools that you could use in a myriad of ways.
Okay. We actually haven't talked so far about boost pressures that we see in these modern Formula One engines. Are you able to give us some kind of insight into what they're using?
So I'll go ahead and say, because things I do know from current field is what people are actually running, so I won't get into that. But say, for instance, so for 2016, we're limited to 4.8 bar absolute. Pretty high boost.
Sorry, you actually did mention that earlier. I overlooked it. So
no worries,
yeah,
no worries.
Yeah. So 4.8 bar absolute. And is it safe to assume that the actual boost pressure up to that limit that is being used is going to depend on power modes, whether it's qualifying session, race pace, or is it pretty consistently run right to the ragged edge of that limit?
I think that would probably come down to team. And if they determined that they thought they needed it for the given power, also, you get in certain aspects of it where you have high altitude, low altitude races. You get one turbo, so the turbos are set up, with that in mind, obviously. But to what extent is each team gonna, set up for which pressure ratio as being a large target for them, with adjusted mass flow rates? One of the other things that comes into the turbo that a lot of people overlook is the VIGVs, which is basically the variable inlet guide vanes. Kind of looks like a camera lens on the front of the compressor. And these, again, nothing proprietary. These have been used. They use them in wastewater pumps and all kinds of other things. What it does is guides the inlet airflow, expanding the compressor map. So helping push you out of surge and helping you, extend your compressor map in higher mass flow rates by guiding the air into the compressor, stabilizing it where it might otherwise have issues.
Sure. Okay.
So that's another tool that they have for these. A lot of tuning options. One of the other things that they currently have that is going away for 26 is they have variable inlet runners. There had been some pictures in a documentary that Honda leaked last year when they thought they were getting out of Formula One for good, went ahead and just did this whole expose to a Japanese magazine and kind of showed everything. But you can see this whole system where they've got these long primaries and this whole active runner length system, and it's really pretty clever to look at. And that's going away. And a lot of that has to do with stabilizing, especially when you're at this point where you're running this lean, the combustion system, and keeping it happy it's a real task. And so being able to chase that and keep it in that same sweet spot across the range, it really changes how it runs. That'll be another one of those 2026 changes. We'll see how it shakes out.
In terms of the other element there, the MGUK, well, actually, coming back to the MGUH, am I right in saying that the MGUH element is also going away for 2026 rules?
It is going away. That is correct. Okay. Just as we're seeing a few production cars come with them, it's going away.
Yeah, I mean, I want to get into, if we have time, a little bit about the road relevance. I won't touch on that right now, but I mean, I can see this being a massive change because if that system, obviously we don't at our level get access to this sort of equipment, but I can only imagine that properly set up with the right control strategies, that MGUH system could essentially eliminate lag completely. And then going to a system with a non-MGUH turbocharger That's going to be a big change for the
Yeah,
teams, the engine design, and then the driving style.
yeah. I'll say the transient response. I can imagine the pedal feel will be quite different. The one saving grace for 26 is with the MGUK. They're bumping it up significantly in terms of its kilowatt input. So some of the strategies might kind of go the way like the McLaren P1 did, where you use your MGUK to be a torque fill. The P1
Mm,
had some bigger turbos and a little bit of lag, so they leaned on their electric motor to fill that torque. And so the driver
okay.
said, "I want power now." All right, well, we'll give you electric power until the ice comes on. So I mean, there are ways around it. And again, I think a lot more of that isn't that the drivers won't get what they want. It'll come down to what's the most efficient way to the strategy you'll use on track.
Yeah, it's interesting getting that insight into how complex these are and the myriad of options that are available. In terms of the MGUK, so you've talked about an electric motor essentially providing drive. So that also needs to be charged, and we hear about the drivers on track harvesting energy as
Mm-hmm.
it's referred to. So can you talk us through how that's used to recharge the battery?
How the harvest is used? It's
Yeah.
essentially you're kind of using the K as an engine brake, if you will. So without getting into specifics, that's the simple of it is the K is essentially then an engine brake. So if you're going in a braking zone, this, that, and the other, the K is then actively gears engaged, engines revving down, the K is pulling it down. Much like when you close your throttle bodies on your car, when you're engine braking, all of a sudden you get this big drop in power. That's going from the K now, and so that's when it gets to recharge. There are also other positions on track where you can have the H charge as well.
Is that recharging only done under braking, or can it be done? I mean, obviously, if the driver's at full throttle and wants to charge that battery, I mean, there's going to be an element of the engine power is going to be lost to charging the battery as opposed to actually driving the wheels. So,
Mhm.
is that another element that's used, or is it purely under braking?
I will say we are getting a bit out of where my side of the puzzle comes in, but from my understanding, if I recall going through the regs, they're not actively allowed to drive the engine against the K, so you can't use it as a generator, if you will.
Okay, yeah, just what I was interested to sort of understand how that works.
I should say under braking. So it's, if they're off throttle, they can't use it as a generator in that regard. So they can't just be sitting there, on a caution lap, just charging up the battery, engine's at full bore, the K is just taking up everything it can. So you can't use it in that regards. You
Yeah.
can use the K when you're actually deploying and trying to accelerate, and you make the trade off of we want to charge versus go a bit faster.
And again, that element of it, I guess, comes down to a lot of the strategy for the driver as to when they're going to deploy, how much they're using, and how hard they want to push that, so that they're not completely discharging the battery and leaving themselves vulnerable to a car that's chasing them.
Yeah, I'd imagine to some extent. Again, these are things that there's a whole host of guys with big brains who write code and do the all the track analysis and strategy. It's a whole other side of the business that goes into that.
And again, obviously, as you mentioned, we're sort of moving a little bit away from your specific area of expertise, but it all kind of becomes part and parcel of the engine. So it's interesting to sort of get some insight into it anyway. Another element of this as well is that the engines have various power modes. And again, if anyone's watched Formula One, you sort of hear the drivers occasionally asking if they can move to a different power mode or whatever that may be. Can you give us any sort of insight into how that works in terms of is it adjustments to boost pressure, or is it adjustments to fuel flow, or a combination of the above?
I'm. This is another one where I'm not 100% certain. I'm not a calibration guy. I know they're supposed to have one map. I know they have modes that they can switch, and it's kind of a loophole in the rules. Much like they're not allowed to have multiple throttle maps. So it becomes one of those where, in my mind, it's probably a energy conservation type of thing, fuel flow conservation. Well, not fuel flow, but fuel mass. You might have certain points of the race where you might want to push harder than others. So I think a big part of that is in strategy. I think that, in my experience, drivers always want all the power they can have all the time. That being from NASCAR, that being from anything, who wouldn't want it?
Yeah, no one's going to ever ask for less
Yeah.
power.
Let me right foot decide when I want it or don't. But there's a whole side of the game where it's strategy. Recently, Hannah's kind of made headlines where she's one of the head strategists, and it's a big part of the game, and that's not my realm. So I dare not
Yeah,
venture
okay.
and misstep there.
One thing that maybe you can give us a little insight into is obviously there's a reliability element that's critical in these F1 engines. There's a certain number of internal combustion engines that are allowed to be used during a season, and if the team has to use new power units, then they get grid penalties, which we've seen, and that always
Mhm.
sort of seems to come up towards the sort of tail end of the season. So, what's the expected reliability of one of these engines in terms of racing kilometers, and how does the sort of trade-off between the power that the engines run at, how does that sort of affect the lifing of the engine components?
So the engines are set. I'm trying to think. So I'm looking at the race stuff for 26, and we've got longer expected life for 26 due to the race increase. I want to say right now it's they're expected to be 6 Grand Prix, give or take, I think, per engine. And what happens is, yeah, as you'd expect with any race engine that's being run hard, and as we mentioned before, knock occurrences do happen. The engines do start degrading and start losing power. Now, the thing with the pool is, say, for instance, Carlos Sainz, great example earlier this year. I think everyone spectacularly heard his turbo let go on one of the races. And so in that case, replacing a turbo doesn't mean a whole new PU. A whole new PU is the entire thing. So they will let you kind of pick and choose what parts were damaged and replace just that. Now, what happens is you end up having, as you hear people refer to, a pool. So last year, if I recall, or at least outwardly, there's so much bluffing that goes on this. Mercedes had several engines in pool for Hamilton, and you strategically take, when you're going to take that grid penalty, just so you can have a banker, a fresh engine for when you put it on, but the penalty's already served for it. So there's a whole strategy in regards to that, and being able to know that you're going to have a fresh engine when you need it, or if it's going to be a track that's really advantageous for your car, you could put in a little bit more used engine that you still know has life in it to get through and not let you down.
Yep.
But you might save that really hot one for a big power track where, well, it's not our sweet spot, so we'll need everything we can get.
Yeah, that makes sense. In terms of that degradation and power that you're talking about, which again, most people could probably figure out that is going to happen over the life of a racing engine. Can you give us some sort of indication across its life, percentage wise, maybe how much power are you losing? Is it 1 or 2%, or are you sort of 5 to 10%?
I honestly wouldn't know because right now I'm not allowed to know what they had. That's part of that. Sakura
Sure.
knows that answer, and I don't.
Yeah.
I'd be speculating. So
On that note, and again, if you could quote sort of what is expected across the grid as opposed to trying to get specific on the Red Bull vehicles, these current generation hybrid F1 engines, what sort of power level are they sort of producing on average?
with hybrid, saying both,
Yeah.
I'd guess in the realm of 900 horse,
Okay.
give or take. If just wild guess.
Yep. Yeah. And again,
Knowing kind of fuel flow rates and knowing kind of what hybrid sits at and what they have for expected cylinder pressures, that sort of stuff.
again, I don't want to try and get too deep into the specifics, but obviously, what power are the engines making is always one of the questions that's on any enthusiast's mind.
So one of the things I did want to go back to, in regards to say like the engine lifing, a big part of it isn't that you necessarily pull the engine because it's not making power. A lot of it is because everything has a fatigue life. In other words, it operates at such a strained level that you can run. It's part of the day job is designing into how many cycles that component can live through at a given average stress before all of a sudden your connecting rod just fell into 2 pieces. Where you hear guys all the time are like, oh, I don't know, it's coming from the Subaru world. Let's go to a blown up transmission. I was just rolling down the interstate and all of a sudden, just fifth gear exploded. Well, yeah, but you've been beating on it for 3, 4, 5 years. How many seasons you've been running this thing? Yeah, it just fatigued out. It was done. It owed you nothing. So that's the bigger part. Is so much of the stuff is designed in to get the job done and not so much more. And occasionally that backfires. It had a little more stress at a given place. Something got hotter than it was designed for. Calibration team ended up making some more cylinder pressure and what the rods were spec'd for, and all of a sudden, you spectacularly ventilated a crankcase, in an improper manner. So yeah,
An improper manner. I like that term. Yeah.
But yeah, so
And I mean, I guess on that note as well, if you over design the connecting rod to take a lot more stress or whatever than it's actually going to need to endure, you end up artificially just making a component that's heavier than it potentially needs to be. Correct?
right, because if you had something that was heavier than necessary, you're carrying that weight around the entire time. And not only is it the weight you're carrying on the car, it is also a very dynamic weight that is reciprocating up and down. You know, at 10,000 plus RPM. It's a lot of energy that you're now using.
So suffice to say, in the design of F1 components inside of an engine, you're not trying to apply a massive safety factor. You're running it pretty close to that ragged edge of what the component needs to absolutely do, and not a lot more.
Right. I would say that kind of holds true for all components of a Formula One car, engine included.
Okay, in terms of when those engines have sort of lifed out in terms of the fatigue life of the components, which you've just talked about, is that just go to the big old pile of Formula One engines around the back of the Red Bull Racing workshop, or are these able to then be rebuilt and reintroduced to the pool?
If something is fatigued out, it's dead. It goes to the scrap pile.
Sorry, what I mean more to that is, would you then go through and replace the rotating assembly, pistons, rods, crankshaft, etc.? Is the block recoverable, the cylinder heads recoverable for reuse?
I'll say it totally depends. Situation. So, for instance, we'll go to the Ford GT. That's long and dead and not intellectual property right now. This EcoBoost V6. The block and heads were all just lifed at 24 hours. Done. All scrapped. Nothing's carried over. Pankel crank. I believe we did carry those over. We had a longer life on the crank. Pistons, of course, replaced. Rods replaced. All those high stressed components replaced. So if there is something, an oil filter housing, sure, we can carry that over. That'll live again. The turbos, sure, we'll put that through 3 engines. Your exhaust manifolds, yeah, those are good for usually X amount of miles, so those will go through 2 engines before they're replaced. But if you're replacing the manifolds, you usually replace the turbo and the wastegates and everything else. So at some point, it becomes a logistic of, well, we're replacing this part now, replace the other parts that go with it, because we don't, in one race, take this off and then replace that, and it just becomes a logistics thing. Oh, we forgot to send the wastegates after we did the Sebring run. Crap. Well, yeah.
Yeah, I guess that makes sense. Ultimately, at least up until the budget caps are sort of come into place, I mean, there's a lot of money in Formula One, and I guess particularly for the more well-funded teams, reusing any components probably doesn't necessarily make a lot of sense if there's budget there to just start with a brand new unit.
I'll even say for the grassroots guy, it's one to take into. This bit us hard when I was with Turning Concepts on their Time Attack STI. In the off season, we're supposed to tear down the 2.5 that the car lived with them. They're supposed to tear down the 2.5 that was in it. It was high compression. Thing was making good power on a GTX 3582 at the time. And it was the 3rd season that same engine had been together. It's supposed to come apart, get torn down, do a mag check, fluorescence check, make sure there's no cracks, no propagations, nothing. The first race we go out that next season at Road Atlanta, so I think it was first practice, 8,400 RPM, crank snaps in 2, takes out the entire engine. And you go, oh, that's $300 OEM crank that had you taken it apart and done the simple check and said, oh, look, this is bad. Let me just replace it now. You save yourself thousands upon thousands of dollars. Likewise, you could have had a crack in the rod or a crack in, pistons like to crack a lot around the wrist pins, obviously, whether they're broached or drilled, that sort of thing. You check them and go, oh, that was a time bomb that was going to cost me a lot more money than a simple teardown in an R&R.
Yeah, 100%. And that stuff is always very easy with the benefit of hindsight as well after that failure has occurred. And as you say,
Yeah.
much more expensive to recover from. In terms of the current engine, and I'm guessing this will go for the 2026 regulations as well, there's not really sort of a free-for-all once the design is sort of done and homologated with the FIA. As I understand it, the specification of the engine is essentially frozen. So if you find that maybe you're potentially a little bit down on power, there's not a lot of flexibility to then go and make further refinements to the engine design in order to chase that power. Is that correct?
So that's only really the case if you're in an engine freeze. So right now they're in an engine freeze. The reasoning was that they wanted the teams for the given cost to go ahead and focus on 26 instead of still being in a horsepower war here and this whole new engine formula that you're trying to develop for 4 years down the road. And I think a big part of it too that FIA did is trying to bring in new PU manufacturers. So I don't think Red Bull necessarily wanted to be a manufacturer. They saw things were going, and Honda wanted to walk away, so they said no one else is going to sell us an engine. We're not going back to Renault. HPP won't sell us any Merc, and Ferrari's definitely not going to sell to us. So let us buy Honda. Yeah, but it's also now brought in Audi, and the latest one I heard is apparently there's a Ford Andretti rumor that they might be pairing up. I'm not putting any eggs into that basket right now. So that's only during a freeze. When say from 2014 to 2022, constantly evolving, finding more power, new piston specs, new injector and pre-chamber combinations and cam combinations, whole new head with a new finger follower layout and everything else that goes along with it. Finding gains in pneumatic valve springs and all the other bits that go along with it. So yeah, they're totally tinkering and constantly evolving at that point. So from 26, they'll go back into it and it'll be back to a horsepower war again. Everybody's going to try and find what they can.
Okay, that makes sense. In terms of the actual development of the 2026 internal combustion engine, again, if you can give us some high level concepts of it, how does that sort of start? Is it sort of all done initially in terms of CAD design, computational fluid dynamics, finite element analysis before anything is actually physically manufactured?
Yes. Put simply. So for instance, before this started, you kind of asked, what I walked into at Redbull Powertrains, and when I had interviewed, it was supposed to be that we were carrying over the Honda architecture and taking over manufacturing and doing some joint thing with Sakura, still making them because we wouldn't have a machine shop up and running yet. And by the time I started, that had changed, and I showed up on day one like, yeah, we don't have anything. Honda didn't want to give any of the IP away. They weren't going to sell it to us at any cost. So we're all here. What's in your brain? We got a blank sheet of paper. Let's make an engine. And that's how it started. When I showed up, it had been kicked off. We already had like the first port geometries and some basic chambers, that sort of stuff, kind of moving along. It was very, very infantile compared to where we are now. So my team works very closely. We're the CAD side largely, driving the actual making the surfaces and geometry, working very closely with our thermo fluids guys. Love those guys. They're fantastic to work with. And it's fun because their brains work on stuff where my brain doesn't. And it's I glean information from them. They have a concept, but they don't know how to manufacture it. There's a way we could do it. And I'm like, oh yeah, we could totally do that. We do this, that, and the other. Like, oh, all right. Well, it's been in my head for 3 weeks. Well, why don't you say it? Like, yeah, let's make some power. So yeah, you start at that point, and they're running CFD and combustion analysis softwares. Of course, GT Power and doing coupled sims of 1D and 2D and 3D sims. And so you start looking at all this stuff. And so you start with a very base one cylinder. There's no point in looking at three until you have one that's working the way you want. And then you think of that, all right, well, we've done all this analysis. And you go ahead and, all right, well, let's go and make essentially an inline three. So you're going to do a bank. So you're essentially not going to do half of the V6, and you'll run a coupled sim with that. So you see how they behave. For instance, once you've, modeled your plenum, just the internal geometry, you don't have to make the whole thing in bolts. You're just worried about all the critical geometries and how they're going to work together. And you look at your distribution and your flow to all of them and how it might affect, well, this sharp turn is kind of changing and pushing the charge to the outside of this one valve. So it's kind of affecting the combustion efficiency on this one. We're getting this one swirl, this vortex. All right, how do we change it and tweak it and fix things? Hypothetical issue. And so it all starts as just, I'll say, dumb surfaces. It's literally just a surface. It's not a head. It's just the chamber. It's just the crown. It's just the port, the port walls themselves, just the valve geometry. You don't care about the rest because you literally starts from the inside out. And so, yeah, and it goes through there to a CAD model, to FEA, to, CFD running your water jackets and doing all the rest of that. It's, yeah.
In terms of the sort of advances that we've seen in computing power over, maybe the last decade or so, with all of this design work that you're doing in the virtual world, when it actually comes time to validate that with a real running engine, be it one cylinder or the entire V6, how closely does that tie into the results that you've got in the virtual world? Is it always right on point, or do you sort of find some things that maybe the computer missed?
It's not the computer misses. In the simulation world, I have the saying of trash in, trash out. If you have someone putting inputs in and they don't really know what they're doing, you get numbers out and you go, well, yeah, here's my result. But how valuable is that result? What constraints do you have? Is it a realistic input you gave yourself? Or one of the other jokes is, colors for, CFD is colors for directors. It's a pretty picture. Yeah, here you go. And here's, oh, yeah, that looks good. Let's spend money. How much is it? So in our case, thankfully, we've got a really sharp team of guys. And it made some public news. We fired up our V6 over the summer before shutdown. And I can say, thankfully, yeah, things are tracking right on par with where you expect them to be. And it's a good thing to see. And it's reassuring because you have all this time into it. And you finally get it running. You go, all right, cool. We're not crazy. It's all working as expected, Very reassuring.
Yeah, that must be quite satisfying.
Yeah, and then you have the roadmap of all the other games that we're looking to start implementing or are implementing. And you go, all right, let's get the next 2 or 3 tests going and make sure they all line up. And let's combine those together. And then we got this other one and kick off this new engine. Yeah, so it's pretty wild.
Now, in terms of your sort of Redbull Powertrain division, is this quite daunting? I mean, obviously you've got some incredibly intelligent people working within this division who already have experience with Formula One powertrains. But I mean, is it realistic to sort of start from zero and build a product that's going to be competitive with those who have been developing these engines, particularly the hybrid engines since 2014, the Ferraris, etc., the Mercedes out there, or is there going to be a bit of a lag to kind of get the product up to where it needs to be?
I will say we have one focus, and that is to deliver a championship-winning engine in 26. With the team we have, with the resources we have, with the backing, with pretty much no one ever pushes back when we say, hey, we really need this, we need to get that going, we need a machine shop stat. Cool. Well, our machine shops plan to be, coming online next year. In the interim, we're setting this up across the street so we can actually have resources online and we don't have to deal with these delays that we have outsourcing stuff. Like the support is fully there. You've got
Okay.
the people with the knowledge, you've got the leadership that's, finally come in. And I will say it is a big task. Ben Hodgkinson was kind of saying, yeah, a bunch of mavericks, a bunch of crazy guys who decided that you're going to leave where you were to come and try and do this massive task of, all right, you've got 4 years before your engine's on grid, starting from nothing. And we all look at it and go, yeah, let's do it, So it's exciting.
Yeah, I think that challenge, though, for a lot of people would be something that would be worth fighting for as well. And, instead of iterative development on something that's already been out there, proven and winning, starting from scratch and building, as you say, a championship winning engine, that would be a very satisfying achievement, I believe.
Yeah, it's a big task, but it'll be fun.
There have been some changes, though, in terms of the involvement with Honda. I mean, you sort of already alluded to, Honda were going to sell or pass over their IP to Redbull Powertrains, and then it sounds like you said they decided they didn't want to do that. More recently, we've heard that Honda's sort of back in the fold. So can you give us some insight into how that's all going to work with Honda versus Redbull Powertrains?
So yeah, Honda, the FIA knew this. People on the grid already knew this. Honda was still supplying the long blocks, all being manufactured in Sakura. It was still coming over. All of their critical IP and data we don't have access to. That stays on the Honda side. We have guys who go trackside that support engine. Literally set up, plug in heaters, plug in laptops, do the trackside, as I mentioned before, kind of babysitting the engine. Putting in the tune to make sure the thing runs and stays healthy and survives, and takes care of them in that regard. But yeah, as far as Honda being back involved now, they're not really any more involved than they were. We've had HRC on the car this whole year. The season going really well. Honda wanted a little bit more publicity, so they kind of said, yeah, we really want to have a sticker back on the car now, not just HRC. So yeah, that's why you're now seeing the Honda name back on there and on shirts and stuff. So they're kind of back on as a more, not that their level of commitment has changed. Their stuff's still totally separate on the other side. It really has no correlation to my day job. They just wanted a little bit more public eye.
Yeah, that's fine. All right, moving on. And again, I just want to touch on this because you've already clarified the calibration side is definitely not your area of expertise. Just in terms of the process that goes through with an F1 engine, and I'm assuming there's going to be some involvement due to the validation of what you're doing. Is this all purely done on engine dynos, or is there any chassis dyno work, or is the then validation and adjustment at the track required?
Yes.
Okay.
So
Great. Thank you for that.
all of the above. So we have single cylinder dynos, which are quite separate from an actual V6 dyno, for instance. In that single cylinder dynos, so my team, we're in charge of all the single cylinders. We do all the development. Early development, nitpicking at things. It's easier to do refinements and try tests on them because if it grenades, well, it's one cylinder, not a V6. And it's also just cheaper and easier to do. It's easier to take one little head off of 4 bolts as opposed to taking off, even if you had inline 3. That's just that much more work and cost to make each iterative change. So we have those in which the dynos, the engines don't have their own ancillaries. We feed it fuel, we feed it oil, we feed it coolant. It doesn't have any of that. It's literally just, here's a cylinder turning, making power. It doesn't have its own turbo. You get massive pumps, obviously, that are pumping in and simulating airflow to it. And also doesn't have turbines, so you've got, essentially, simplified terms, throttles on the exhaust side to simulate what you need for exhaust back pressures and make it simulated running conditions that you're trying to test. Then the V6, obviously you'd have a V6 engine, just a dyno, hook the engine up and run it. They then also have gearbox dynos where you kind of run the whole drive lane together. Then you also go a step further. The ERS side then also has their whole side for where they're going to run NGUKs and of course, there are gas benches for turbos. There's all kinds of different things that are going on where you have all this stuff. And you put this whole kit together and you start running it. Yes, so you can run the full kit on V6 dynos and on gearbox dynos when you're at that point. then it also goes off to this really cool thing we have that's called VTC, Vehicle Test Center, where it is essentially kind of this holy grail glorified chassis dyno, all four corners turn, kind of like a rolling road wind tunnel meets a chassis dyno. It's as you guess, kind of the closest thing you get to simulate without actual runtime.
Sure.
And then, of course, there's still the guys trackside who put in the calibration each day and make the adjustments for the different tracks, different altitudes, all that sort of stuff. So it's the full gambit.
In terms of, there's a couple of videos that I've really enjoyed watching from I think it might have been the V10 days, and one of them's from Renault with one of their engines on a transient dyno, and essentially they're replicating an entire racing lap, and it's running through the engine RPM and simulating the downshifts and the gear changes. Is that a technology that you also use, those transient dynos?
Yeah, that's it. It's pretty standard for everyone. Yeah, at this level.
Is that used as a tuning calibration tool, or is that used as a reliability sort of endurance style test, or is it again all of the above?
Kind of both, yeah. Definitely a durability thing. Say, for instance, you're running a given engine spec that's at the track, and you're sitting there doing a simulation of that given track, and you know that, hey, that's the next track that's coming up. You know you're already been running that track, and you're going to see how the engines hold up and what issues you're having, any tuning issues you might be having, simulating altitude corrections and things like that. And again, durability things. All of a sudden something props up where, hey, we cracked this piston we shouldn't have. Oh, what was in this last batch? Where's the material certs? What's going on? Is this through all of them, or is this an isolated incident? Oh crap, the engines at the track might have this problem too. So yeah, it's definitely a durability thing you do ahead of time, so you don't run into those 911 issues, those emergencies.
Sure. Just circling back as well, we talked a little bit about the fact that the current engines are under a sort of specification freeze. From what I understand, there is still the ability, if reliability problems are found, to make modifications to the specification to improve reliability. Is that correct?
Correct. So if someone has a problem where say they started running a hotter tune and were constantly cracking pistons, they could put in a request to have a piston change. Or they have happened earlier this year, printed high pressure fuel flow line developed cracks because there'd been a flaw in the print that wasn't captured. Well, put in requests so that we could wrap them in carbon fiber and isolate them shaking so that crack didn't propagate and cause a fuel leak. Things like that. Little things. It can be little things. It can be big things. So it can be from any nuanced, oh, we had to change this clearance because the manufacturing ended up having this problem, to we need a whole new piston because this is not working.
I assume there's a sort of a bit of a fine line there that you'd have to work with the FIA to prove that any changed part is purely a strength and reliability change, and there is no performance gain to be had from it.
Correct. So yeah, you have to have approval from the FIA, and the changes that are made are then, I won't say they're published, they're distributed through the teams. Everybody knows who's doing what changes. And so usually the images you get of said changes are this very, very, very micro view of this one chamfer here is changing for this reason. You don't see anything else, so it's,
Yeah.
of course you sit there and start thinking, well, what could that be? Oh, that's, I worked there. That's this part. That's, the nose feed on this crank and this, that, and the other bit. And you're like, oh, yeah. And then they start drawing on a piece of paper. Yeah, it goes like this and this is here. Yeah. So
They're trying to get some level of transparency throughout the teams, but also still keeping the IP nice and locked down and secret.
Yeah, so it's the screenshot that the team releases, but the FIA distributes it so everybody knows that, hey, this change happened. Yeah, that sort of thing. So yeah, a lot of it's so cloak and dagger and chess and bluffing and who's doing what, and yeah. So
on that note, and this probably goes a little bit deeper than our core topic, but I'm assuming there must be quite a level of trust between the teams and the FIA, with the amount of information that the FIA have on the engines that doesn't go any further. Is it locked down that the FIA don't really have an in-depth knowledge of what's inside?
No, the FIA knows everything that goes on in the engine. Like they come in and want full prints of everything and CAD models of everything you have going on. They actually have oversight of that. Even so, working at Red Bull, there's firewalls that are up for how much we can know about Red Bull or any other given team, and that's already been in place, for instance, with AlphaTauri. So AlphaTauri being owned by the same, there's a wall between them, so they can't have transparency, and AlphaTauri can't just copy what's going on at Red Bull, and vice versa. and particularly as a PU manufacturer. For instance, so the quote unquote war room, where all the strategists go when they're in Milton Keynes versus guys at the track, and they're on this giant screen, and you see them all looking at computers going through data. We have to have our own war room. We're not allowed to be at the same war room that they are because we are a PU manufacturer. We're not allowed to see the data and have the information they have. So it is, despite what the rumor mill thinks, quite segregated.
All right, Micah, let's move towards wrapping this thing up. It's been a great chat, but we do want to sort of respect your time here. We've got the same 3 questions we finish all of our interviews with, and the first of those is, what's next in the future for you? I mean, clearly, obviously, we've already talked about the 2026 engine, but do you want to expand on anything there, your direction, where you sort of see yourself in the future? Is F1 going to be you for the foreseeable future?
Yeah, we'll see. Moving to Milton Keynes spin adjustment. Still trying to get my wife over here. She's still in Mooresville, North Carolina right now, so it's been a bit of a strain. But for foreseeable future, learning a bunch of cool stuff here. It's a cool project. I still have other side projects I'm doing. Still tinkering with the McLarens with the shop back in North Carolina, so that's actually one of my excitements. I still have a land speed Subaru that I want to do. It's an EJ10 D-stroked 1 liter. And of course, now being over here, I want to put a pre-chamber in it for giggles, but so that's on permanent timeout right now. So we'll just see where it goes. We'll just follow it one day at a time.
Is there any advice that you'd give to a younger version of yourself, or maybe one of our listeners, that could help you reach where you are today in your career, maybe a little bit faster? Maybe if there's any pitfalls that you think you could have avoided, or anything you should have done earlier in your career that would have fast-tracked things?
So I'd say one thing is I had in my head, kind of like a lot of people, like, oh, how do you get to F1, this, that, and the other? You just apply. One of the things I had in my head is, I just thought race teams, this, that, and the other. I don't have enough knowledge or enough experience to go be on a race team and do this, that, and the other. And I waited a while until I finally applied at Roush Yates, and got over there. I was 30 at the time. And so I should have just gone ahead and wanted to go racing, just applied with a race team earlier, and I didn't. I'd spoken with HPD way back out of college, but that was a deal that fell apart because there's no way I could have lived in California for what they wanted to pay for a college graduate. But I tell it, just go for it. Really, that's it. Just, if it's something you want to do, pursue it, try it. What's the worst that happens? They're going to tell you no. And the other thing I realized is at this level, we've got people who are junior and fresh out of college, super smart, top of their class sort of guys. And then there's guys like myself who've been around the block and kind of did it the hard way and worked at a machine shop, moonlighting after hours and done it kind of the roundabout way. So just go for it. Don't hesitate.
Yeah, I think that's really good advice. As you sort of mentioned right at the start, I think particularly F1, people sort of put those teams up on a pedestal, but as we mentioned at the start, they're still looking for people with a certain skill set, and if you've got that skill set, well, it's obviously going to be a potential match. So absolutely nothing to be lost in applying and seeing where you go. I think the other thing is, not just Formula One, but all of these areas of industry, you're not going to necessarily walk into a job with the exact complete skill set that's going to be needed for the job, and there will be some level of in-house on-the-job training as well. So don't be scared because you don't think that you have everything sort of locked down that you'll need for a position.
And I think that's true for any job, period. If you're looking at a job and you're looking at this job and you knock everything out that they want, you should be applying for a higher job than that, because no one expects you to hire someone coming in that 100% can do everything for that given role. There's always some amount of training, some amount of learning that's expected.
Yeah, absolutely.
So yeah. And also for the other guys, real quick on that one, I get a lot of LinkedIn messages and Facebook messages and Instagram messages and et cetera, whatever. A lot of young guys want to know how to get into it. Get into a race team. You might not start at Formula One. You might start with an IndyCar team. You might start with a NASCAR team. You might start Australian V8 Supercar. You get your foot in the door. Get started. Have a background going, and it makes it easier to progress on up. So don't think you have to swing for, I'm going to start at Red Bull. I'm going to start at Mercedes. Yeah.
Yeah, I think that progression through, even from grassroots, race teams, and then moving up through the ranks with the more professional teams, that experience is going to really stand you in good stead to get positions at those sort of upper echelons of motorsport. Absolutely. All right, our last question for today: if people want to follow you and see what you're up to, maybe reach out, how are they best to do that, Micah?
Oh boy. Best, you can find me on LinkedIn. Usually I try to keep that to a professional level. Ginger Micah. is my at handle for Instagram. You can usually find me there. That's usually where I'm posting things. Or 3MI Racing. You can also find that on there or on Facebook. It's a little bit
Perfect.
slower these days, but yeah, you can find me there.
All right. Well, we will link to those accounts in the show notes and make it super easy for people to find you.
Awesome.
All right, Micah, been great to chat. Great to get some insight into the world of Formula One powertrains. We really appreciate your time, and we'll look forward to seeing how the Red Bull stands up in 2026 with these new engine rules.
Yeah. Thanks for having me. I appreciate it.
If you enjoyed this episode of Tuned In with Micah, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt anywhere in the world. Also, this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to DillDog92 from Australia, who has said, "Tuned In is the best. Absolutely love how informative and interesting this channel is. Constantly looking forward to each new episode. Keep up the great work, HPA." Well, thanks for the kind words there. If you reach out and get in touch with your t-shirt size and shipping details, we'll fire a fresh tee straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.